Hello, welcome to Meki Teki. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement of creating these kinds of technical videos in public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me a spark of creating these kinds of technical videos in public domain. And I would like to thank Almighty my God for my good health and broad mind. And I would like to thank my friends, followers, my dear students and subscribers for their continuous support and encouragement. Today's topic of interest is kinematics of fluid flow. Okay, what is meant by a kinematics? A fluid kinematics is a science which deals with the fluid particles in motion without considering the force. Okay, so without considering the force, if the motion of the fluid particle, let us see. So this is the fluid particle. It is having a motion in all the three directions, say x, y, and z directions. If the motion of the fluid particle is studied without considering the force we have not considered. So, force we have not considered, that is called kinematics of fluid flow. If the force is considered, if the force is considered, that is called a dynamics of fluid flow. So that much simple about the difference between the kinematics and dynamics of fluid flow. Here, the motion parameter involves the acceleration as well as the velocity and the discharge of the fluid flow. Acceleration, velocity, and discharge of the fluid flow. Here, in the discharge, the mass is involved. In velocity and acceleration, time is involved. So, with these parameters, we are describing the fluid particle. So, that is the uh, basic thing about the kinematics of fluid flow. Okay, so with this introduction, I will move on to the kinematics of fluid flow. Here, our interest is either we have to find velocity, acceleration, or discharge of a fluid flow with the helps of different kinds of an approaches as well as the different kinds of a different dimensions. We will find those parameters. Let us see the first one, which is the continuity equation for three-dimensional flow in Cartesian coordinate. Let us consider a fluid particle like this, a, a rectangular prism of a fluid particle having a dimensions of dx, dz, and dy, having the dimensions, the length, width, and height of the fluid particle. And this fluid particle is having a motion, like say this is an p into v, sorry, rho into v into dx into dz, and this is the rho into u into dx dy dz, and this is the rho into w into dx dy, or the this is the parameters involved. The density of the fluid particle is involved, the velocity in the directions are involved, and the areas, so dx and dy, say, or dy and dz, we can say. So the density, velocity, and the areas are involved in the motion. We have not at all find the area, we have not at all find the force, but the parameter with the velocity is being found. So if a fluid particle is, I say, in x direction, in the x direction, rho u dy dz, when the fluid particle came up the another side, it will become it will become rho plus d rho into dx into u plus du by dx into dy and dz. This rho on u, this rho on u had been convected with the velocity parameters. This is the differential in velocity. So this term, the difference in velocity term. So here, like that, all the three directions have to be find out, and the equation, the continuity equation of the three-dimension parameter will look like after all the numerical integration and differentiation parameters, the final equation be like this: the dou rho by dou t plus dou rho u divided by dou x plus dou rho v divided by dou y plus dou rho w divided by dou z, which is equal to 0. Here, dou rho by dou t, it indicates the fluid is in. If it is equal to 0, the flow is in steady flow. If it is not equal to 0, the flow is unsteady. Here the density and the velocity, density rho into u, u, v, w are velocity parameter with respect to different axes, and x, y, z are the coordinates. So for u it is for x coordinate, v it is for y coordinate, w it is for z coordinate. So this is our basic idea about this continuity equation. Okay, so from this equation, for the flow is steady flow, dou rho by dou t is equal to 0, then our continuity equation becomes without this dou rho by dou t, it can be written like dou into rho u by dou x plus dou into rho v by dou y plus dou into rho w divided by dou z is equal to 0. If the flow is incompressible, then rho becomes constant. Therefore, our continuity equation becomes dou u by dou x plus dou v by dou y plus dou w by dou z. It is for three-dimensional flow. If we consider for the two-dimension, either one of the component can be eliminated and other two components can be used. So for the one dimension, that is dou u by dou x is equal to 0. So with this equation, we are finding out the continuity equation. The continuity equation, it says it is for one dimension. Let us consider it is a steam tube of varying sections in the section 1 and 2. The section is vary, the path is vary, but what it say is the mass flow rate, is being constant over the flow. So that is the indication of the continuity equation. The mass flow rate is constant. That is, the mass flow in the section 1 is rho 1 a1 v1, and mass flow rate in section 2 is rho 2 a2 v2. So rho av, that is the mass flow rate. Okay, so here what it indicates, for the steady flow there is no increase in the mass within the control volume. That is why the mass entering per unit time is equal to mass leaving per unit time. So mass remains constant. So that is the equation which derives by the continuity. So continuity equation is derived by means of the invented by Archimedes. So Archimedes is the brain of the continuity equation. He said that the m1 mass entering the system, which is equal to mass leaving the system. Since it is a control volume, there is no chance of escaping the mass. So that is the thing. Therefore, m1 difference in mass, dm divided by dt with respect to time is equal to m1 minus m2. Here the m is nothing but rho av. So with the section 1 and section 2, we have indicated that rho a1 v1 is rho a1 v1 minus rho a2 v2 is equal to dm by dt. So for the steady flow condition, dm by dt is equal to 0. Therefore rho 1 a1 v1 is equal to rho 2 a2 v2. Therefore rho 1 a1 v1 is equal to rho 2 a2 v2. This is derived from the above equation. Rho a1 v1 minus rho a2 v2 is equal to 0. So for the incompressible, again the density is equal to constant. Therefore the a1 v1 is equal to a2 v2, which is nothing but volume rate of flow. So this is a mass rate of flow, where this is the volume rate of flow, because the density remains constant. So a1 v1 is equal to a2 v2, that is nothing but a discharge of a system. This unit is meter cube per second. The unit of the discharge is meter cube per second. Okay, so therefore according to the continuity equation, it is conservation of mass. It is conservation of mass. How the mass is being utilized for the steady flow of incompressible fluid is being calculated. The volume flow rate remains constant from section to section. That is our understanding about the continuity equation for one dimension. So the next one is the approaches in fluid flow. We have two types of approaches, kinematic approaches in fluid flow. One is Lagrangian and another one is Eulerian. In Lagrangian method, an individual fluid particle is being selected, and we are going to absorb this individual fluid particle in every course of its motion through the entire space. So this Lagrangian approach is a controlled mass approach, since each and every fluid particle is being selected for studying the motion parameters. And in an Eulerian approach, it is an control volume approach. Eulerian approach is a control volume approach. In any point in a space occupied by the fluid is being selected. Here have to know this difference better. If a location is being selected, that is Eulerian. If the fluid particle is being selected, so that is Lagrangian. So in Eulerian approach, any fluid, any point in the space occupied by the fluid is being selected, and observations were made. The change of velocity, density, pressure at each and every point has been taken care. So that is why it is called control volume approach. So if you know better, if you want to know better, so these lines are formed as by Eulerian approach, and this is a line made by Lagrangian. Hope you have understand that the individual fluid particle is being selected. So this is the flow stream. If the particle of individual particle is being selected, so that is a Lagrangian approach. If the stream is selected from this point to this point, it is called Eulerian approach. So Eulerian method are commonly used in fluid experiments or analysis. A probe placed in the flow. So a probe is placed in the flow for measuring at different times of pressures or velocities or anything else. So here the acceleration of the fluid particle have to be known. So for this you have to know better about the velocity and acceleration relationship. So the velocity is equal to ds by dt, that is change in displacement with respect to time, and the acceleration is change in velocity with respect to time. So the velocity components in x, y and z directions are u. U is the function of x, y, z and time, and v is the function of x, y, z and time, and w is the function of x, y, z and time. Therefore, by differential calculation, if it is an infinitesimal change of u, the three dimensions are being taken care. That is why Here, dou, the partial derivative, dou u by dou x into dx plus dou u by dou y into dy plus dou u by dou z into dz plus dou u by dou t into dt. So this is for the acceleration. This is the total acceleration of a fluid if it is the total velocity, and finding total acceleration, the local acceleration is coming to picture. That is why it is being indicated. And the acceleration component, we know that dou u by dou t. Therefore, in the equation u for the a acceleration in x direction, which is u into du by dx plus v into du by dy plus w into du by dz plus dou u by dou t. Here, this is the total acceleration of a fluid, and this term is the convective acceleration, and this last term is the local acceleration. The total acceleration is nothing but the sum of convective acceleration and the local acceleration. If it is a steady flow, there is no local acceleration is there. So, if it is assumed to be a steady flow, there is no local acceleration. Only the convective accelerations are there. I hope similar. It is similar to x and x, y, z. So all the directions are similar, where the velocities are different. So these velocities are different. Instead of in the x direction, it is dou u. In y direction, it is dou v. In z direction, it is dou w. You have to clear about this. Okay. So finally, after all the approaches, we are describing the fluid particles. Either it follows a path line or a streamline or a steam tube or a straight line. First of all, we have to know what is meant by a timeline. A timeline is a in different times, in the different positions, in the different times and different positions, how the fluid flow is behaved. That is called the timeline. So that is called as a timeline. At t is equal to 0, what is the velocity, acceleration, and the continuities in the time A, as well as the time B, as well as the time C, and so on. So we are finding with respect to the time how the fluid flow is behaved. So that is the called timeline. If it is a path line, it is very simple. Fluid particle at some intermediate time, which is called path line. The path traced by the fluid particle, that is called path line. If it is a streamline, the streamline represents the tangent of the streamline represents the velocity of flow. So that is our interest. The tangent of the streamline represents the velocity of flow. So here, the velocity of the fluid particle is this. If we draw the tangent, it indicates the velocity vector in that direction. If the number of streamlines are flowing in a tube or form a tube, it is called stream tube, where the streak line is the line which is traced similarly to the continual motion of the fluid particle away from the object. So that is called a streak line. So it represents a motion of a fluid particle in different range, laminar, turbulent, all the ranges are have been incorporated in the streamline. For the better understanding of the streamline, if we lighting a lamp, if we lighting a lamp or a candle, if the candle is producing a smoke, the smoke is a very good example of the streak line. So the production of the smoke from the candle is a very good example of the streamline. If you notice that up to the some distance, it will be like a very steady flow. After that, the small disturbances are happen, and it continuously dispersed. So that is the form of a streamline. I hope you have understand these lines better. Okay, so with this I'm going to stop today's session. If you have any doubts, please let me know in the comment section. Or if you are interested in watching more videos, please like, share, and subscribe my channel Make It Techie with Santhosh. And for it give, if you like more, if you comment more, if you subscribe more, it will give a greater encouragement of creating these kinds of technical videos. So with this, I'm going to thank you once again all. Thank you and bye bye from Santosh. Thank you.